the third main principle of object-oriented programming next to data abstraction and polymorphism is inheritance. Inheritance is based on the observation that data abstractions are often very similar, especially if the entities they represent are similar, such as a person versus an employee, or a car part versus an airplane part, and so on. So here's a simple example. I'm taking the concept of a collection of elements. So this is a multiset, a collection with no defined order where elements may be repeated. For example, the coins in my pocket. I can add a constraint to this. I can add an order. This turns it into a sequence where I have a first element, second element, up to last element. I can add another constraint on how elements are added and removed. I can add on one side and remove on the same side, and that turns it into a stack. Or I can add on one side and remove always on the other side. That turns it into a queue. This gives me 4 data abstractions that are related according to the diagram here. Now, it's important that the language support this. Why is it important? Well, because of duplication, duplicated code. And this is a problem at 2 levels. If I have 2 similar abstractions and most of the code is the same, then I have to maintain them both. And this doubles the amount of work, and they may diverge with time. This is introducing low-level bugs. That's the first point. The second point is a high-level point. They may be expressing the same or similar ideas. Well, why should I express the same idea twice in a program? It would be much better to represent it exactly once. So that's the point. And inheritance can achieve this for similar abstractions. And the way it's done is that the definition A can inherit from B. So that means A will use B as a base, possibly with modifying and extending it. And the incremental definition is called a class. This is the same term that we used for the complete data abstractions we defined earlier. So a class in object-oriented terminology can be either a complete or an incremental definition. But the resulting definition, for example, an incremental plus all the pieces, all the classes it depends on, together always forms a complete definition, of course. Now, inheritance can be a very useful thing, but it is also extremely dangerous. The issue is that if we can extend a data abstraction with inheritance, in fact, we have another interface to that data abstraction, an additional interface to the usual one of the operations. This second interface is extremely difficult to make it correct and to maintain it correctly throughout the lifetime of the program and the abstraction. This is what experience shows. It's a very subtle interface. So we have to be very careful. And in fact, there are 2 general rules that I'm going to explain. One is you prefer composition over inheritance whenever possible. And 2, when using inheritance, you should always follow a particular principle, which is called the substitution principle. Well, I'll explain in a minute. So let's say we're using inheritance. The first point, we want to use it as little as possible, as I said. For example, we can use it in well-defined ways, in programming patterns. There are well-established lists and books of programming patterns. And another point is when we define a new class, we should declare it final or not extensible by inheritance by default. The default is that we don't want to have to handle this problem. And a third point is that whenever possible, we use composition instead of inheritance. And practice shows composition is often sufficient. So what is composition? Composition is a very simple idea. Composition means that an object will refer to another object in one of its attributes. Very simple. So for example, the compound figure class, in previous example, has an attribute called figlist, and this attribute contains references to other objects. This is an example of composition. No inheritance necessary. And the point is that if we use composition, we are not adding another interface. The object that we refer to from inside another object is always accessed through its usual interface and never by extending its interface. So that's why composition is preferable over inheritance. So here's a simple diagram. So on the left we have inheritance. A inherits from B, and object OA is an instance of A. So that's the case of inheritance. And the right we have composition. So we have A and B have no inheritance relation. OB is an instance of B, and OA is an instance of A. All we have is that inside of A, we have a reference to the object OB. So that means A simply uses OB to do its work, but it's not extending the interface of OB. So this is much easier to use than inheritance. Okay, so that's the first rule. The second rule is the substitution principle. This principle is extremely important, and if you really want to use inheritance, you must follow this principle. If you don't, all bets are off. So suppose that A inherits from B with objects OA and OB. So A inherits from B, and A is an object OA, and B is object OB. So the substitution principle says that if we have a procedure that works with OB, then it must also work for OA. If we have a procedure that works for objects of a given class, it must also work for objects of subclasses. If this principle is followed, then inheritance will not break anything. We say that A is a conservative extension of B in that case, if we follow it. This principle is also called the Liskov substitution principle. In fact, this is the same Barbara Liskov who invented clue.